Section 2.3, Forces. In this section, we are going to talk about what makes an object move. We've had words that describes an object that stays in the same position with time. For example, the potted plant on the table stays in the same position after some time has passed. We say that that is not moving. We say that the change in position is 0, or we can say that it's stationary. If after some time we came and the potted plant is now on the other end of the table, we can use some of our moving words to describe that. You can see that there was some speed or velocity as it moved across the table. And since there was a change in the position, if there was a change in velocity, we may even have an acceleration. The fact is that something caused a potted plant to move from the left to the right. The thing that caused that change in motion was a force. A good definition for the force is that a force changes an object's motion. You may have seen some of the loose definition around defining a force as a push or a pull. This is correct, but a more accurate description is to change an object's state of motion. If it's in rest, it's going to make the object move. If the object is moving, it's going to change its motion, either increase or decrease its velocity as it's moving. So let's list some facts about forces. Forces are vector quantities, which means that they have both magnitude and direction. The unit of force is a Newton, which is named after the scientist Isaac Newton, and the letter N is the symbol that's used to represent that unit of force. Forces can cancel each other as a result in a net force or total force of 0 newtons. And forces acting on an object can be drawn with arrows. As we can see on this blue ball, there are 4 forces acting on it, and the length of the arrow indicates the larger force. So from looking at these arrows, we see that moving to the right, we have a larger force, and pulling the ball to the left is a smaller force in the opposite direction. In addition to that, we have different types of forces. Frictional force opposes the motion. You see these blue line forces shows the direction of motion of the sled. The red lines indicate, or the red arrows indicate the direction of the frictional force. Gravity force is the force that pulls object towards the earth due to the force of gravity. An applied force is any force that's applied to get an object moving or to change its motion. A spring force is the force that's exerted on the coils of a spring to get it moving. The drag force is the force on an airplane that would cause it to either lift up or land towards the earth. The normal force is a force that is as a result of a reaction between 2 surfaces and the forces that's exerted on one surface by another. The magnetic force is a force that exerts between the north and south poles of a magnet. And the electric force is a force due to the charges on an atom, for example, or the electrical charges. Now let's focus at force along one single direction. Let's take the horizontal direction. And we have a basketball here with a force of 100 newtons pushing it to the right, and another force of 100 newtons pushing it to the left. Let us describe the force moving to the right, that arrow with 100 newtons is shown, and the force that's moving to the left, which is the arrow that's pointing in opposite direction, let's give that value of negative 100 newtons. We do that to represent a difference in the direction. So here, the negative 100 newtons tells us that this force is not less than, but is in the opposite direction to this force that's a 100 newton force. So now we've represented those forces and directions in terms of a positive and negative sign, and then we can combine them to get the net force, or the sum of all the forces. So we get 100 plus the negative 100 newtons, and that's 0 newtons. So the net force acting on the basketball is 0 newtons, and as a result of no net force, the ball will not move. The ball remains stationary. Inertia is defined as the resistance to a body's change in motion. In the first picture, we have a person standing using his phone, and the bus is suddenly moving, and he's in a bus. The bus suddenly moves out from under him. Because of his inertia, his body's resistance to change in motion, it appears that the person falls back. but really what's happening is his mass, the person, has an inertia which is very resistant to the change in motion of the bus as the bus is being pulled out from under him. Similarly, a girl seated in one of the seats will find that her hair gets pulled back or dragged backwards because of the inertia of her hair and its resistance to change in motion. It really wants to stay in its original position. So if a body is at rest, or if it's moving at constant speed in a straight line, it will remain at rest or will continue to move at constant speed in a straight line unless it's acted upon by a force. And that force has to do with how much a body changes depends on the inertia of that body. So let's look at falling objects. The scientist Galileo Galilei did some experiments on the Leaning Tower of Pisa where he dropped two objects of different sizes. He measured the distance that the object fell and looked at the speed at which the object fell when they hit the ground. He discovered two things as these objects fell, that both objects fell at the same rate. It didn't matter if one had a larger mass than the other. The fact that they fell at the same rate indicated that mass was independent to the rate at which it fell. Both balls increased in speed as they fell. So as we know, increasing in speed means an object is accelerating. That acceleration we were able to determine is 9.8 meters per second squared. And so the distance d that an object falls is given by 1/2 times the acceleration times the square of the time that the object was falling. Now we have horizontal motion and we can have vertical motion. For example, an arrow just being released from the air that's falling vertically towards the ground. We can tell that the velocity of the arrow is increasing because we see that the length of the vectors are increasing. So we know the magnitude of the downward speed is increasing as it falls with an acceleration of 9.8 meters per second squared towards the earth. Now we can have motion in two directions. For example, now the arrow is being shot off with a horizontal velocity as well as a vertical velocity. As the arrow is shot with a horizontal velocity, that velocity remains constant because there's no force along the horizontal direction to change its motion. However, we know that there is an acceleration due to gravity downwards, and so the object is accelerating towards the earth, as you can tell by the change in the vectors here as they get longer. This means that when we have these two motion together, we call them compound motion. So the arrow is going to continue out in the air and will really technically quote unquote land, which is really when the velocity, vertical velocity, increases enough to get the arrow and bring it down to the ground. Now we'll talk about Newton's laws of motion.